For this question, number 3, we're asked to look at the following sequence of reagents used and predict the final product of the reaction. This can be confusing at first, obviously, because there are multiple reagents we need to consider. Their regio and stereochemical outcomes of each reaction can lead to differences in the product obtained for the next reaction. So how I would go about this is go along the sequence and then finally put your final product in. We have ample space, so we're going to scroll down over here and write out our starting compound. It's bicyclic, and students tend to have a lot of problems with bicyclic systems, obviously, because they have to think in 3 dimensions. So in the first reaction, we have O3 and DMS. Now, O3 and DMS is a specific ozonolysis type of reaction that only occurs in alkenes, so thankfully we have an alkene to the left. And what it does is it cleaves directly down the double bond and installs oxygens, creating ketones. So you would slice that down right the center and use ketones, or replace the alkene with ketones at that point. Now, you can either draw this in a 3-dimensional perspective, or you can draw it in 2 dimensions. If you choose to draw it in 3 dimensions, you can maintain the 3-carbon system like that, draw the bridges down, because that's what we've done, and then we can cleave this double bond and rotate it to form our aldehyde or ketone. In this case, it's an aldehyde. And so this is the 3-dimensional view of the product, but if you wanted to draw it in a planar format, one representation can be seen like this. So there's a hydrogen protruding off of there, hydrogen protruding off of there. Okay, so these 2 compounds are equivalent, and that's what we've done for the first steps. Then we're going to use excess lithium aluminum hydride and water. So this is a reduction reaction. Lithium aluminum hydride in excess, so we're using more than one equivalent, and then a protonation step using water. Now we have our aldehydes over here, which can be reduced down, and that's what lithium aluminum hydride attacks. So you reduce your aldehydes down into hydroxyl or alcohols. So your base stays the same. The way these stereochemical projections remains. And instead of having aldehydes, we reduce them down into alcohols. In the final step of the reaction, we use excess PBr3. PBr3 functions as a reagent to substitute out our hydroxyl groups for bromines. Keep in mind that this is an SN2 reaction, so if you had a stereocenter connected, then you would have inversion of that. But because we don't have one in this case, we can go ahead and draw out the products where that's a terribly drawn pentagon, but that's okay. Where the alcohols have been replaced for bromines. Okay, so keep in mind that the way you draw it is important, and keeping in mind stereochemical outcomes can be important for the final product and whether you get all your points. So we can go back over here and add our final product. It's a 5-membered ring. With bromines on it. Now for the next reaction, I would suggest you do the same. I'm going to try and get out my eraser tool and hopefully, yeah, there we go. Erase all of this out. Maybe Oh. And we can continue on with the next reaction. So here we're treating our compound with PCC in CH2Cl2. Now this is an oxidizing reaction. PCC is a moderately strong oxidizing reagent, and it's going to oxidize a hydroxyl into a ketone or aldehyde depending on the carbon it's attached to. You can see here is our hydroxyl group projecting out, and it's connected to a secondary carbon, so we're going to get a ketone. And if you want, you can draw this out stereochemically. For simplicity's sake, I'm going to draw it out normally as a planar projection. So that's our methyl group here, and it's 1, 2 carbons away. So 1, 2, and our hydroxyl group becomes a ketone. So that's the first step in our reaction. The second step and the third step go together. The second step involves using a Grignard reagent and water. So a Grignard reagent, the CH3 is going to function as CH3 minus, a nucleophile. It's going to attack the carbonyl center, the carbon, and kick off electrons onto oxygen, thus adding carbons to your compound. And then finally reducing your ketone down into a hydroxyl group. Following that, we're treating it with concentrated sulfuric acid, H2SO4, and heat. Now, because this is an elimination reaction, you have to consider all beta positions, which I'm going to draw out in blue. So if this is the alpha position that contains the leaving group, the beta positions are 1 away from that, so that's beta 1, beta 2, and beta 3. Now, because concentrated sulfuric acid usually gives us the Zaitsev product, we're going to look for the most substituted beta position, pull off a proton from there, and then kick off the OH, which will be kicked off as H3O+, and you get a double bond. But what you need to consider is who's more substituted, and thus you'd pull off a proton from there. But because B2 and B3 have the same substitution, you can get 2 products out of this reaction, and those are a 5-membered ring with a methyl group. Your OH leaves, you have another methyl group over here, and this is one with a double bond between B3 and the alpha carbon. Or you could have gotten this compound with a double bond between B2. Now these 2 compounds are not equivalent to each other, obviously, so you need to continue this reaction with 2 different products in mind. Now the final step is using KMNO4, sodium hydroxide, and you're doing this in colder conditions. This is a syn reaction, so syn dihydroxylation should be the first thing that comes to mind. I'm going to abbreviate to syn di-OH. And because you have different products, you can choose which one you want in this case. I'm going to draw out one of the products. You guys should try and draw out the other one. We have our 5-membered ring with a methyl group that's unaffected by this reaction. You've got a stereochemical projection with an OH. Another one on the same configuration because they're syn. But remember that the methyl group still exists on the same carbon, so it needs to be on a dash. Now if you drew it for this compound over here, you'd have a similar outcome, but remember your OH wouldn't be on this position, it'd be over here somewhere. We're going to work on the next part of this question, where we're dealing with this halide that also contains a hydroxyl group, and we're going to treat it first with PCC and CH2Cl2. Again, we've seen this reaction so many times at this point, you're probably tired of me talking about it. So I'm going to go ahead and just draw out what the product would be. That is an oxidization or an oxidation reaction. I just got to make sure I'm going to draw out the appropriate number of carbons here, because in class, when I talked about this, I fortunately drew out the wrong compound and everyone got confused. So I'm going to call it oxidization right here, and we're going to convert that group, specifically the hydroxyl group, into an aldehyde. So that's the first step in the reaction. The next step, again, you're looking at a Grignard reagent, so you're adding carbons. In this case, specifically a CH2, or rather a CH3 group. So Br and you're reducing the aldehyde down into a hydroxyl group. And the final step in this reaction, which is the most important step, I'd say, we use NaH. Now, keep in mind that NaH functions as a base. In the context of what you guys have learned so far, NaH deprotonates a carbon and then you have loss of a leaving group. But when NaH is present with a generally acidic functional group, like OH, you have a competition reaction where the H-, the hydride ion, deprotonates the H. Following deprotonation, this oxygen right over here bears a negative charge. It's a nucleophile. You have a carbon here that, because of this bromine, is partially positive. It's pulling all the electrons away. So this oxygen is really inclined to attack the carbon and produce a cyclic compound. I'm going to use green here because people find it difficult to draw out cyclic compounds. So you would number, if the oxygen is attacking the carbon, that means this oxygen is definitely part of the ring. So it's position number 1, 2, 3, 4, 5, and 6. Oxygen at position 1 is attacking carbon at position 6. So you draw out a 6-membered ring. You number it in such a way: 1, 2, 3, 4, 5, and 6. But remember that position number 2 here has a methyl group projection, so we need to draw that on our final compound to get the right outcome. So here, this set of reagents leads to the production of a 6-membered ring with a methyl group projection off of a particular carbon. It's a cyclic ether. Now let's get the writing out of the way so we can focus on this last part, which is pretty interesting if you haven't done a question like it thus far. So I can find the cursor. The first reaction involves treating it with excess, so more than one equivalent of Grignard reagent, where the nucleophile is CH3-. Now what does this do to an ester? It's interesting because the first round, you have a CH3- attack the carbonyl group, it kicks off its electrons, but subsequently to that, the electrons from the alkoxide push down and kick off this group as a leaving group. So you essentially open up the ring. Now following that, you still have a ketone present because you formed a double bond again. Another CH3- group attacks and you form your hydroxyl from there. So because the ring opens, we should number the ring 1, 2, 3, 4, and 5 in such a way that when we open it up, so from here, the first step in the reaction is excess CH3 MgBr, followed by a second step with water, H2O. And from here, you get out, if you wanted to draw it without opening it up, that's understandable as well. So this hydroxyl corresponds to the ketone. So we have 1, 2, 3, 4, and 5. So we opened it up. Now, the final step is treating it with chromic acid. Na2Cr2O7, H2SO4, and water, H2O. You got to keep in mind that this reaction can only take place where there's a either primary or secondary alcohol. We have a tertiary alcohol towards the very end, right here, so that's a location that cannot be attacked. However, this location is perfectly fine because it's a primary alcohol. But recall that primary alcohols can oxidize twice. And so your end product is actually going to be a carboxylic acid with an alcohol at the very end. Actually, so the carboxylic acid is going to be here. And if you were to expand this out, you could draw a 1, 2, 3, 4, 5 carbon chain. So 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. At the 5 carbon, you've got a carboxylic acid, right? 1, 2, 3, 4, 5. And in position number 2, you've got a methyl and an alcohol. So that would be your final product.